Okay, let's start another lecture for Calc 2. Parametric equations and polar coordinates. That is the second section, Calc with parametric curves. So it means if you are given those equations, what can you say? What are the things that you can calculate? Now remember, curve. What did you have for a curve? So if I had like graph of a function, say. I could talk about tangent to the graph, say, I could talk about, say, area under the graph, and I could talk about length of this curve. So, tangent, area, and length. These are the three things that we study in this section, and we find formulas for these three things using parametric equations of the curve. Now you know the formulas for all three of them when in fact this curve is a graph of a function. Remember, graph of a function. We are not talking about graphs of functions. We are just talking about curves. You see the curve can be as strange as this thing. So can you tell me that? Can you say what function really defines this? No, there's no function. Can't be graph of a function. It just the vertical line test fails here. It fails the vertical line test dramatically. So what can we say about this? How can I find, say, length of this thing? How can I find tangent at some point to this curve? Well, the area under the curve is another story. Well, okay, anyway, the first thing is the differential. So what is the differential? So if I have x and y functions of t, I didn't write x, t, and yt for some reason. So dx dt is the f prime, dy dt is g prime, as you can see. And this prime is not with respect to, say, x or y, it is with respect to t. So this prime is with respect to t. Then, as I said, and I said again, that dx dt can be treated as a fraction. So we have dx equals f prime t dt, and dy is g prime t dt. So the differentials are these two. As an example, this here, I don't know if you can identify this. It's good to know that this is in fact a circle. Well, what circle is that? That is a circle x minus 2 squared plus y minus or plus 6 squared is 16 or 4 squared. Now, I did not discuss how to go from these equations into an xy equation, or but I probably will do that at some point. But you can just take a look at there's no general rule anyway. So dx will be the derivative of this. Derivative of this is minus 3 sine 3t. So that is 3 times 4. That's minus 12. And the other one is in fact cosine 3t. So that is 12 cosine 3t dt. So these are differentials. Let me keep that because I need the differentials to define or to find some formula for tangent. So first is tangent. So equation of tangent of the line tangent to a parametric curve at a given point on the curve. Now, how do you give a point on the curve? Identify a point. Either you give the xy or you give the t, right? So this is given t, or simply x and y. But if you are given x and y, I said simply, but that's not simple. In fact, given t is much better. And you will see why. So that is the problem equation of the line tangent to a parametric curve at a given point on the curve. So this given is given t or simply given x and y coordinates at that point. But in any case, we need t. Remember, we need that t, and you will see why. So, what was the equation of tangent? Equation of tangent was, so equation of tangent. So what do we need? We need slope, right? So we need dy dx, right? We need dy dx, change in y divided by change in x. This doesn't mean that y is a function of x. No, dy dx means change in y divided by change in x, infinitesimal changes. But we have that dy dx over there, right? So the dy from here is g prime t dt, the dx is f prime t dt, the dt can cancel out, so I have g prime over f prime. Or you see the g prime and f prime are these two. So this is you can write the dx, dy dt first, dy dt on top, and divide by dx dt. Okay, so either that is in fact, now some people can remember this one easier because it says it's like you are dividing this by dt and dividing this by dt. If you can remember the g and f, g prime f prime, it is simply the derivative of y with respect to t divided by the derivative of x with respect to t. That's all. Now, this is general form of slope. Right? So we have slope as a function of time. That's amazing. We have slope as a function of time. So we need slope at a certain point in time. And if we have xy coordinates, we can just write equation of tangent line. So if we have this m, so this m, which is, this m is in fact a function of time. See, this dy dx is a function of time. So we have the slope as a function of time. Okay, so let me give you an example of this. What I mean by slope as a function of time. So, example. So let's say we have say x is say, let's go with the one that we had here, cosine 3t, and y is 4 sine 3t. And let's say t is between 0, I need 1 revolution, so I need 2 pi over 3, right? So when I multiply by 3, I will get 2 pi. Okay, so that's 1 revolution. And now, m as a function of time is dy dt divided by dx dt. So that is in fact minus 12 sine 3t, and this one is simply 12 cosine 3t. Simplify, I have minus tangent 3t. Minus tangent 3t. So that's amazing. That this is in fact slope, which is this is in fact this circle is 4 and it's going fast. So the tangent is tangent, and it's interesting that it is tangent of 3t. It's tangent of this angle minus tangent of this angle. So when it is at 0, tangent of 0 is in time when this starts at the 0, and then this point in fact and then goes up to here, and then pi over 2, we see that when we're here, that is infinite, right? Slope is, no, 0, sorry. Here, that's 0. And in fact, it's not at that point that is 0. Well, anyway, so that is the general formula. So we can say that the slope at any time is that formula. Slope at any time is that formula. And I have made a mistake, and I'm just thinking this can't be tangent. No. Please don't make this mistake. This is a common mistake. What was the mistake? I was thinking this can't be it. It's wrong. So that's dy dt, not dx dt. This derivative, this one divided by this one. Common mistake. I made that one. I'm glad I made that mistake. So you can see that even I make that mistake when. So that is in fact derivative of this one, which is 12 cosine 3t divided by minus 12 sine 3t. That is minus cotangent of 3t. In fact, not tangent. That's minus cotangent. And at this point, when t is 0, it's infinite. You see, this is a vertical line. Vertical line has slope infinite. And here it's horizontal line, and that has a slope 0. So that is slope as a function of time. See this, when it's moving, the slope of this tangent line is changing, right? Slope of this tangent line is changing. That's what I'm talking about, the slope as a function of time. Okay, so now if I ask, so what was common mistake? Common mistake was it is dy dt over dx dt, not what? Not dx dt over dy dt, which I wrote first. Okay, so don't make that mistake, and you saw that I made that mistake, so everybody is prone to this common mistake. So, because it's the first one, you usually I just look at this thing and say, oh, that's, no, it is this derivative of this one divided by derivative of this one. Okay, so, now let's give another example of how to find tangent line, and for example, find an equation for the line tangent to, say, x equals let me think what I want to go with cosine 4t. Cosine 4t, and the y is sine 4t at point 1 square root of 2 over 2 square root of 2 over 2. Okay, so this is the situation that the point is given to you, and not the time. So first thing you should do is to find the time, the t, for which this particle is at this point. So just you imagine the particle is moving in a circle. That's a circle. You can tell that it's 40, 40, they are the same. And the radius, radii, or this arm, are the same, but the r is 1. So that's a circle with radius 1. But that has omega equals 4, so that's faster than omega equals 1. Anyway, so that is, let's find it. So if it's square root of 2 over 2 and square root of 2 over 2, first thing find time. Time t, for which we have cosine 4t equals square root of 2 over 2 and sine 4t equals square root of 2 over 2. Well, it's easier to deal with tangent. So this it gives me, if I divide this by this, it gives me a tangent of 4t is 1, right? If I divide this one by this one, then I will get tangent of 4t is 1. It's easier. So what angle has tangent 1? Well, it's pi over 4 and what's that? The other one is 5 pi over, is it 5 pi over 4, I guess, yeah. 5 pi over 4. So 5 pi over 4 gives me minus and minus, so that's the fourth quadrant. So this is in fact pi over 4. So this tells me that 4t is in fact pi over 4 and the t is pi over 16. So at time pi over 16, this object is at this point using this motion. So the object at time pi over 16 is here. Now let's find what am I going to? Oh yeah, find the equation of the line. So what do I need? I need m, right? I need m. So let me. I should erase something. Maybe I just erase this thing. So let's go up here and. So let's come up here. So I have t equals pi over 16. I need m as a function of time, and that was dy dt over dx dt. Don't forget. So that's this one divided by this one. So that is the derivative of this one is 4 cosine 4t divided by minus 4 sine 4t. So that's minus cotangent of 4t. So m at pi over 16 is minus cotangent of, cotangent of pi over 4, right? Cotangent of pi over 4. Minus cotangent of pi over 4, this is 4. So that's minus 1. So I have m. And I have the point. So I have point and m. Remember the equation of a line when a point and the slope are given to you. So this gives me that y minus y0 square root of 2 over 2 equals m, which is minus 1 times x minus x0. Remember that formula where space somewhere. Well, I will write it when I erase all these things. So that is equation. You can do it like this, or you can simplify and get some nice formula for that. Y minus square root of 2 over 2 is minus x plus square root of 2 over 2. And if I move this to the other side, I will get is minus x plus square root of 2. Okay, so that is the equation of the equation of the line tangent, because you might have different equations. So different, say, type of equation. Say you can even write the equation in parametric form. So okay, so that is equation of line tangent. That's how you do it. If you are given t, you're lucky. You can find both point and say slope, and write the point slope equation of the line. And if you are given the point, you can find time, and you can do the same thing. Okay, so that was the story of tangent line. There are some interesting questions that one can ask. Say, you might be given something like an equation in parametric form, and you're asked for what time or at what points on the graph you have a vertical or horizontal tangent line. Okay, So given parametric equations of a curve, we can ask many questions. So one of them which is common is tangent line. So these are notes. Tangent line is a vertical. It's like this when m of t is infinite, or plus minus infinite. It's infinite in a sense. I know plus minus. So you have to see where if that mt has a denominator. If that mt has a denominator, then denominator equal to 0 will give you t. So we can say if mt is like a function, say rt divided by say st, then st equal to 0 gives t for which mt is infinite, and it can be plus or minus. So that's tangent line vertical, and tangent line is horizontal when what? When mt is 0. So if mt is again rt over st, then rt equal to 0 gives t for which mt is 0. Well, in both cases, be careful because this might give you 0, 0. If that happens, in fact, it's like at that point, the curve is discontinuous, which means there is no tangent at that point. So be careful. That might give you both 0, both numerator and denominator 0, which means a tangent line is not defined. So when I say a tangent line is horizontal or vertical, I mean it is defined. There is a tangent line, right? So, for example, for this, which can be graph of absolute value of x, there is no tangent line here, right? There is no tangent line. Or for this thing, say, what is tangent? I mean, you might say, okay, there's one this way, one this way, or here we can say one this way, one this way. But there should be just one, right? So when a curve has a corner, if you are able to write down some parametric equation, then it might give you 0 over 0, something like that. So it's ambiguous. But anyway, most often we are given nice, in fact, amazingly nice, say equations, and you are asked to find the vertical and horizontal. You can do that. So that was the story of a tangent line. Next is say area. So that's B, area under the curve. Well, this one is, I should leave this, in fact the book should have left this to Calc 3. But let's look at it and then I will tell you what to do. So let's say, what was the area under the curve? Area under the curve was this. You had the dA, this is the dA, right? This is the dA, this is the dx, right? And what is this? What is x? So if this is x, this is y. Right? Since we are assuming that x and y, none of them is the function of the other one, so they are like independent, but we have the x, there's change in x. And with this change in x, there might be some change in y. So what we have here is this. This dA, if I look at it carefully, this dA, look at this way, it is y and this is dx, So it is y dx. So one is intimidated to say, okay, so area is in fact from t0 to t1, say y dx. No. If you do that, you might get 0. And say, gee, what happened? There's this big area here, so what's going on? In fact, one should use Green's theorem. Using Green's theorem. And that is multivariable calc. So don't say what is Green's theorem. I just write a formula for you here. And remember, this can go both ways. So if I have something like a curve like this, say, it can go this way too. So you can have either this or this. X dy, either y dx or x dy. So in either case, that gives you something. What can we do? In fact, that Green's theorem is some kind of average of these two. Some kind of average of these two. So using Green's theorem, we have this. And that area will be integral of, if I remember correctly, y dx minus x dy. So these are the same in fact. So what should I do? I should divide it by 2. And 1 minus, because one of them is negative to the other one. So it should be 1/2 here. And it shouldn't be, say, negative. So let me double check the formula. I have written somewhere here. Yeah. So that is wrong. It should be x dy. X dy not y dx. So this one goes first. So if you use this, you will get a positive number, and that positive number, in fact, is the area. But I showed you, each one of them is in fact the same. Some people like to just take this one and put absolute value because it might be negative and then say, yeah, that's area. But there's a danger to that, so be careful. It should be like this. So I leave this to you it's simple. I wrote dy and dx for you at the beginning. So just write down if x is g ft, then this will be f prime t dt, and this is like gt f prime t, and something like that. So you will get something like this if x and y are given as x is given as ft and y is given as gt, then area will be something like this. And from t0 to t1 something, x will be f prime, no, x is ft, dy is g prime t dt, minus the t0 to t1, then the other one will be gt f prime t dt, okay? So it's something like that. It's simply, but I'm not saying that the integral is nice, no, but it is not hard to find. I mean, you can simply write down the integral and use something like Mathematica, for example, or Wolfram Alpha to find the integral. Anyway, so C, which is related to us, we can write down the formula easily, and there is no controversy. We don't need Green's theorem, and that is arc length. Arc length. Remember when I started arc length, I drew a picture for you like this, and I said, okay, this is my DL, and then I have dx here and dy here, and I said dl squared is like dx squared plus dy squared, and so dl was square root of. Well, let's use this. So going from t0 to t1, the arc length L is integral from t0 to t1 of square root of dx squared plus dy squared. Remember the dx dy I wrote for you? That is integral from t0 to t1. This was f, I guess I used f, so that's f prime t dt, f prime t squared, let's put squared here, plus g prime t dt squared, right? So there's dt squared, so I can move that dt squared out, and underneath I have f prime squared plus g prime squared. Outside I have dt. But remember, the f prime was dy, dx dt, and the other one was dy dt. So I can write this in this form, t0 to t1, and this is dx dt squared plus dy dt squared dt. This formula is much better than the other formula, which is 1 plus f prime x squared dx. Remember that? Square root of blah blah blah. I like this. In fact, this is amazingly important when it comes to physics and higher level mathematics. This arc length formula, and you will see that in Calc 3. Okay, so let me find arc length. I will find the circumference of a circle. Okay. So, an amazing example, because if you wanted to find circumference of a circle using xy, you have to write down the equation of the circle in 2 parts. Well, that's okay, you can find half of that, but that's not easy to find. I mean, so, an important example is this. So if I have a circle with radius r, it's easy to just put it here and radius r. And when you're doing things like this, write down the simplest equation, simplest parametric equation. Don't write 40, 50, blah, blah. No, just t. So this has x equals r cosine t, remember, and y is r sine t, and for t between 0 and 2 pi, that gives me 1 revolution. So length of this, so this is t0 and t1, they are the same, so t0 is 0, t1 is 2 pi, right? So that's 1 revolution. So this length of this curve, which is circumference, is in fact from 0 to 2 pi, square root of dx dt squared plus dy dt squared dt. So what is it? It is, let me go here. So dx dt is r sine theta minus r sine t squared, right? Dy dt, that is r cosine t squared, dt outside. So this is integral 0 to pi, square root. I have r squared comes out, right? And the sine t, cosine t, I have sine squared t plus cosine squared t, and outside is dt. And well, let me continue here so everybody can see. So that integral will be simply 0 to pi. Cosine squared plus sine squared is 1, so I have r squared here. So that integral is 0 to pi r dt. R is a positive number, so and that gives me r t from 0 to 2 pi. So that is 2 pi r. That is like among the very first formulas that when you were in like elementary school they gave you. That's the circumference of a circle is pi times diameter. That's 2 pi or pi times 2r. 2r is the diameter of the circle, so 2 pi r. You can try and write down the equation of the circle. You cannot write the equation of the whole circle as a function of x, y as a function of x. You have to divide it in 2 and write the equation for this one. And then remember that formula was 1 plus f prime x squared. That is just something. You can try that. But you see, when I write it in this form, then that's fantastic. It is an amazingly nice, say, way of finding circumference of a circle. And remember, I guess we found the area of a circle a long time ago. But you would say that even finding area using other, like, say, polar coordinates is much easier than using xy coordinates. So, let me circumference of an ellipse, say. So let's say we have a nice ellipse in xy plane, and this is point O, and we have a minus b and b, so this has equation x squared over a squared plus y squared over b squared is 1. Parametric equation, remember, x is a cosine t and y is b sine t, and we can say that t goes from 0 to 2 pi. I need derivatives of these two, so I need dx dt. Remember that is minus a sine t, and the other one is dy dt is b cosine t. So length will be an integral from 0 to 2 pi square root of dx dt squared plus dy dt squared dt. So that is from 0 to 2 pi. If you write that, that's a squared, well, let's write it. So I have a squared sine squared t plus b squared cosine squared t dt. Now this is what we call an example of an elliptic integral. An elliptic integral is like a function. So that's like a function if I write 0 to say t, for example, or s something, and that's the function of this s, if that's s, and that is a function, elliptic integral, like ln, which is an integral. Ln is the integral of 1 over x dx, and this is a function. Elliptic integral gives me a function, and that's just amazing. The length, arc length of this is a nice function, in fact. A nice function. You can graph this thing, but you can Google online and see what an elliptic integral is and where it comes from. It comes from here. It comes from circumference of an ellipse. Okay, so that is, I guess, what I wanted to say. Let me check and see if there's anything else. So, area and that's it. So, I might give you some examples of this, especially one of them is quite nice, an example of parametric equations for something. And so let me stop here and see you next time.